Okay, good afternoon, everybody. I hope everybody's having a wonderful day. So today we're going to be picking up where we were last day, where we were talking about Turing machines. In particular, I showed you a little bit about the so-called Church-Turing thesis, which naturally characterizes our conception of an algorithm, the one that you may have been using for many, or possibly some years in your studies, as Turing machine-based algorithms. And I talked about how there's many different equivalent models of computation. And for any one such model like that, you can always replace those models with the one for which is equivalent to a Turing machine. And that's another equivalent way of talking about an algorithm, which is a very eye-opening kind of experience to have. So after that, I talked about the notion of simulating a Turing machine using another model of computation. So suppose I give you some variant or some Turing machine that has some more features to it. And what my goal is I'm going to show you how you can take that new model and simulate it using a Turing machine. And the way we did this is we show that there's some equivalent set of moves that I can make with this Turing machine that's simulating the other machine, just like what we did last day. So remember last day I showed you how I can take a Turing machine and I can implement that stay option for the tape movements. So instead of having just left and right, I can have it so it stays. So I showed you how you could do that with two moves. So remember, I just go left, then right. It was really nice and simple. So I'm going to be doing more of that today. And the goal here is I'm going to keep showing you more variants of Turing machines until I get to a point where I'm going to start really showing you things that really sound kind of sketchy to sound that they could be equivalent to a Turing machine. So we're going to be building ourselves up with more and more things that we could do with our Turing machines, okay? So I thought I would start off first by stripping away features that our Turing machine may have, considering so-called restricted Turing machines. So here's a couple of examples of such things. So the first one I have here for you is suppose I have a Turing machine where its head never moves left of the original position it starts. So what I mean by this is, remember, if I have my input W that's put on the tape head starts right here, right? What I'm telling you is that we're going to forbid it ever from going that way. It can go this way, but it never can go past this initial position. So it can go left or right, it just can't go left that direction. Another way you could think about this is so-called a semi-infinite tape. What does that mean? Remember in a Turing machine model that I presented to you, you could go left or right as long as you want, right? In contrast here, there's only one form of infinite in that one direction. It's only to the right here, right? Pun intended. So with this model, you might ask, okay, well, how do I get that this is equivalent to a Turing machine in the way I gave it to you? You could do this actually with tape tracks. So for example, you could have it, for example, where you have it where if you had your two-way, where it could go all the way to the left, all the way to the right, what you could do is you can model those left and rights all the way to one direction to another as multiple tracks. So you could have two tracks where one is going to be the first one in moving one direction or two directions from this origin spot, or you can have it going to the left one direction or two directions and so on. I have the details. If you're curious more about this, you can find details about this one, if my memory serves me correctly, in the Hopcroft book. But if you find yourself curious more about this, you may, if you have the Sipser book, you might know and recognize this version. This is actually how Sipser defines the tape in their book. So if you're curious about that, see, like I said, some people define the Turing machine a little differently than we did. So this is one version. You don't lose anything by doing this, for example. Another version here, this one's actually a little easier for us to see that it's equivalent to our model, is suppose instead of having it where I have, so suppose I have my tape. I don't know, say this is my input W. And we know to the left and the right of it, there's always blanks. and so on. And say I have, I don't know, x0, x1, x2, x3, x4. Suppose I have these symbols here that is part of my input here that I put onto the tape. So what we would like in this model is never to have it so we forbid the algorithm from ever writing to the tape a blank. So, for example, I can't have it so that the tape head, say right here, it makes this a blank and then goes left or right. I'm forbidding that from happening. That can't happen. Does anybody have any ideas of how I could simulate a Turing machine that has this property? Any ideas? Think of the first thing you can think of, and you're probably right. So remember, the point here is that I don't want to have it so it ever writes blanks to the tape. So remember, the blank is part of the tape alphabet. Well, there's one suggestion about tape. What would we do instead of the blank, though? What would we do instead, though? What do we need to do instead of a blank? What can we do? Remember, I get to choose how the Turing machine that's going to simulate this thing looks like. So instead of a blank, what should you do? Any ideas? So I'll give you a tip. Remember, it's that we never write a blank to the tape. So what would I do for my Turing machine that's going to simulate this? Yes, you can still read the blanks, but you can't write them. So think about it. Think about it. Think of the first thing that comes to mind. If I can't write blanks, what can I do instead? Think about it. So suppose instead of writing a B like this, I wrote, I don't know, like K. Like maybe I write K here instead. If I make my Turing machine so it interprets the K's like B's, is that still okay? Yeah, that's perfectly fine. That's exactly what you do here. So instead of having it where you write blanks, you write another symbol that you put in your tape alphabet. That's it. So that's how you'd simulate such a Turing machine. So you don't actually need the feature. So you can get rid of the fact that it could write blank. You can put another tape symbol on there. So those are a couple examples of ways I can kind of strip down the features of the Turing machine. And I could still have all of the abilities I had before. There's other versions of Turing machines where I could strip away other features. Those are very good things for me to ask you on an exam. So just keep that in mind. So I may ask you at some point, hey, explain to me how I could do this with a Turing machine. That's a very good kind of question. Put a star on this, okay? This is something I'd like to ask. Now, I want to, instead of restricting the model of the Turing machine, I want to actually build it up now. I want to buff up this thing like I was doing last day. So I'm going to consider what we're going to call a multi-tape Turing machine. So what is this? This is a Turing machine with a finite control that has a state. So it's going to have its state just like a Turing machine, but now instead we're going to have multiple tapes. The number of tapes I'm going to call K. So each tape will have cells just like before. However, each of the tapes has its own head. So each tape will have its own tape head. So here's how the setup is going to work. Is the input is going to be placed on the first tape. So whatever we call the first tape, that's the first tape. Now all the other cells will have blanks on them just like we had before, except now I have multiple tapes. Now, the head of the first tape is going to be in the exact same spot you would expect it for the regular Turing machine. It'll be in the first position, leftmost on the input. However, the heads of all the other tapes, they're going to be arbitrarily placed. And you might ask, so just keep that in mind. The head could be somewhere else. They aren't going to all line up at the beginning, but it may as well be the case because of the following fact. Remember, these tapes go infinitely to the left and to the right. But what's on all the other tapes? Can somebody tell me what's on all of the other tapes? What's in every cell? What's in every other cell? What symbols on all of the tapes, except for the first one? The first one may have other things. Yeah, they're all blanks. Exactly. So if you think of this as infinitely going that way and infinitely going this way, it doesn't really matter, right? It doesn't matter that the head could be wherever. As far as we're concerned, it may as well be the first position we're pointing at. So just keep that in mind. So the heads could be sitting wherever. So here's a picture to help you see what I mean. Often when people talk about multi-tape Turing machines, they often will define what K is. So for example, if K is equal to 3, I'd call this a 3-tape Turing machine. So I have my finite control just like I had before, except now notice that I have 3 tapes. And the way that these tapes are going to interact is actually quite similar to the way you would expect them to work, because each one of these tapes is going to operate independently. So if you were to have K is equal to 1, you would have exactly what you had before with our Turing machine. However, I need to describe to you how this stuff works with all the other tape heads. So remember, the big thing I want you to point out here is that these tape heads, they can all move left or right they're all moving independently of one another. So this actually gives us a lot more functionality if you think about it when I want to describe things to you. Because now I have it so that I could, for example, just to give you an idea of what kind of things you could do with this. Remember the problem of trying to recognize palindromes? Just to give you an example, I may revisit this example at some point. Suppose I had the word like race car on the first tape. What I can do is I can copy from the first tape all of the input to the second tape, and say if I have only 2 tapes. What I can do is I can have, so one of the tape heads reads them from front to back, then the other one from back to front, and I have it scan going left to right and the other one going right to left. If I end up getting matches on both of those, you can definitely convince somebody that that's indeed a palindrome. So that's an example of how you could use one of these multi-tape Turing machines to do things a little easier. So you don't have to do don't do a whole lot of this crazy, like you've seen how we had to use the Turing machine very often, where we did the zig and the zag back and forth every time, right? You could conceivably do the same exact thing here, but I could save myself a lot of transitions and moves by having this additional tape to keep track of more information, just like in the example I just mentioned. Does everybody see that? So that's one neat feature about the multi-tape Turing machine, is that I can still copy and write things just like I did before, but now I have this tape head that I can use and I can move them around. So I'll give you the description of how a move works with the multi-tape Turing machine, but does everybody get the general idea first before we get to that? Is that I have these tape heads, they can move left or right. I think I have them also so they can stay in the same spot. Yep, I have it so that they can be stationary too, but like I said, it's not necessary. But it's very common multi-tape Turing machines define it so it also can have the stay option. So notice that this thing has a lot of features to it. So that being said, let me describe how a move works with a multi-tape Turing machine, just so you have some familiarity with what it is. I'll encourage you to think about how you could formally write down the multi-tape Turing machine based on what I'm going to describe here with the move. So I'll leave that more as an exercise for you to think about. The multi-tape Turing machine on a move does the following. So it does the following. So believe it or not, it's almost going to be exactly the same. Just there's a little bit more to it. So like I wrote the first time I defined a Turing machine, it's going to first change state. It may change state. That's the first thing. It may change state. It may be in the same state as previously, right? That may be the case. For each of the tapes, a tape symbol is written on its scanned cell. So just to be clear what I mean by that, on each one of our moves, the Multitape Turing machine will scan each of the cells that the head is currently on for each of its tapes. So it's going to write that symbol, and then naturally, what do you think the third one's going to be based on how we defined a Turing machine? What do you think the third thing it's going to do is going to be? Any ideas? Well, we already have writing in step 2. Step 2 is where we're going to write. So what's the thing we do after we write to the cell? Hey, no worries. No, that's, yeah, it moves. Exactly. It's going to move. But now notice that we have multiple heads. So then each tape head moves. I just about wrote head. Moves. That's when you know it's a Friday. Moves left, right, or stays stationary. So I'm going to incorporate that stationary move. The heads move direction independently. So for example, some of the tape heads, they might move left, some might move right, some might stay. And this would actually be baked right into what the transition function will tell you. So instead of, because remember, our definition of the Turing machine transition is always I have a state and I read the symbol on the tape, right? The way it works with the multi-tape Turing machine is you're going to have a state, then you're going to have for each of your tapes, you're going to have the input, the tape symbol that you have read. Does everybody get that? So every time I need to look at each one of those tape cells for each one of the heads of the tapes, that's why I need to describe to you some K. That's why we have a K when I tell you it's a K-taped Turing machine, right? So I'll let you think about how I could write this down. Like, the hint I can give you is it basically looks exactly the same, except now I'm going to have to include some exponent K somewhere, at least once. But I must stress that like a Turing machine, a multi-tape, I was about to write multiple. A multi-tape, I was trying to expand this out a little further. A multi-tape Turing machine accepts by entering a final state, just like what you would expect. By entering a final state. I'm going to switch markers. This one's a little spotty there. My apologies. Let's see how this one does. So here's the theorem that I want to present to you, is that you might think, oh, look, we have all these tapes. We have the stay feature as well. does this do anything for us? And as I suggested the other day, the answer is no. It's still going to be equivalent to some Turing machine. Is that every multi-tape, okay, this marker isn't any different. Every multi-tape Turing machine has an equivalent, I'll just be clear what I mean by that, one tape Turing machine. In fact, I think this one's even worse. Let me just switch to another marker. Let's try this one. This one, I have a good feeling about this one. Okay. If you want the full proof for this one, I'm going to provide it to you as, if you find yourself looking at the Hopcroft book, I believe it's in both of Sipser and Hopcroft. I have the cross references in the notes, so if you find yourself wanting to look into this in more detail, there's a couple of different ways you can prove this. I'm going to give you the idea that's in the Hopcroft book. So let me just give you the idea of how you would do this. So I'm not going to give you all the details, but I think this picture will help you see exactly how you approach this. So, you know how I told you last day that you could encode tape symbols as tuples, and those tuples could represent tracks on our Turing machine. In fact, let me give us a little bit more space here. So suppose I gave you, just for the sake of me showing you this picture, so suppose I had a 2-tape Turing machine. You know, it'll have its finite control, but it'll have 2 tapes. And suppose I have my 2 tapes, and just for the sake of convenience for myself, I'm just going to assume that the tapes are lined up. That's a part of the proof, by the way, is that you have to keep track of some additional information about the left and the right moves that happen between the tapes. That detail I'm not going to go into here. I would recommend, if you're curious about that, go check out the full proofs. So here's an idea of how I would go about this. So suppose I had the word like cat right here, and I don't know, this was say right here I have dog. Say it's cat and dog like this, and the first tape head is pointing me right here, and the second head is, say, suppose it's right here on the O. So one way you can go about this is you can use, so if I have K tapes, you use 2K tracks. So notice I have 4 tracks here because I have 2 tapes. And if I wanted to encode this information on here, what I could do is I'll write it like this, but note that the order you do these doesn't matter too much. Just the order in which the tracks occur does matter. So suppose I have cat. Actually, I think cat I want right here. Cat. Let me move cat here. My apologies. And I want dog right about here. So these are going to represent the information on my 2 tapes. But you might ask, okay, well, how do I store the information about the heads? Here's how you do it. You can make markers. So for example, the first head, have it point right here. You might put a star. To make it easier for you, let me write it in binary. I'll say 1, 0, 0, 0, and suppose it goes like this. Keep in mind, remember, this is still the 1 tape Turing machine. Just remember, I'm just using tracks to encode these things as multiple tape symbols. So what you do is you take one of these and read it, starting at 0, A. This would probably be a 0 here. I think I have a 1. I have the head pointing at the O. But this is effectively how you would store the information of the 2-tape Turing machine. Is you'd have 2K tracks, you would have one track to tell you where the head of the first tape is. The second one here, just to store the information of the first tape. The third one here is just for the location of the second tape head. And the last one here I just have for the second tape's information. So the way this works is when you go left or right, that's the tough part of this proof, is simulating what happens. So for example, if I have the head pointing at one of these here, then how does it affect the other tracks? So I hopefully gave you just a general gist of how you would encode the information onto one Turing machine, just like this with a single tape. But if you want more details about how the moves happen, I'd recommend you take a look at this. Is that okay with everybody? So here's the general idea. Is that kind of cool? So I can encode those tapes using tape tracks. And then just the matter of figuring out how you move left and right depends on how you read what's going on in these tracks, which that's the tricky part. In fact, if you look at this, it looks kind of interesting in its own right, because if you read off, say for example, you imagine you're right here. You'd want to have some way of knowing, okay, so suppose my tape head moves right on this one. I need to change this 1 to a 0 and then move that to be a 1, right? Well, I would need some mechanism to be able to check, to go down here and update this particular symbol. But the way you might think of that, if you're doing this, say, in a programming language, just thinking off the top of my head here, you would imagine I have to scan through this down like this through each of the tracks, right? That's one way you might think of trying to do this. And that intuition actually matches what you might try doing in terms of how you would actually look at how many moves are going to be necessary to simulate one move of the multi-tape Turing machine. Because remember, one move of the multi-tape Turing machine includes all of those moves with all the heads and writing all of those tapes simultaneously. Here, you're going to actually have to do much more work. So this should give you an idea of how that we don't actually get anything new. It's just a feature. Kind of like when we talked about the epsilon NFA versus the NFA. Way back when, we've seen it more as a design feature. It makes it easier for us to design things. But you also, but I want to mention one other detail that's going to be relevant for us later on in the course that I want to touch upon, but I'm not going to go into too much depth about it at this stage. But I want to define time complexity for you, for a Turing machine. Because I have one more theorem I want to say about this, just in connection with what I just mentioned. So let me just define quickly what I mean by time complexity. So I'm certain you've seen this phrase before, many times before. If you've taken some algorithms classes, I guarantee you've seen this many times. So I'm going to just define this in the context of a Turing machine. So if I give you the input W, I'm going to say that the length of W is n. I'm going to call this the input length. You might know this is a phrase called input size when I encode the instance onto a tape. So just to give you a little bit of a hindsight about this. The running time, that's supposed to be an E, by the way. It sort of melted. The running time of a Turing machine on input W is the number of steps. And when I say steps, I'm talking moves. The number of steps M takes before halting. Now, this naturally is going to come up next, is how I define time complexity of the machine itself, because I've just described it for you for a given input. The time complexity of M So the machine is a function t of n. Keep in mind, it's just a name for a function. Doesn't have to be called t. That is the maximum over all inputs w. Can somebody tell me, what does that match up exactly with from your analysis of algorithms kind of stuff? What did I just describe to you here? What kind of analysis is this? Yes, it's worst case. It's worst case analysis. Perfect. Yeah, so I'm trying to figure out, okay, well, which ones take me the longest for a given length n? And that's exactly worst case analysis right there, just sitting right there. Wonderful. Yeah, so one thing you'll notice very quickly is I've just defined it for a machine in general. So notice that because of the way a Turing machine works, it's very possible that t of n might actually be infinite. So you have to be very careful, because if I give you some Turing machine and it doesn't actually halt all the time, its time complexity is actually infinite. It's unbounded. It's never going, you can't guarantee it's going to stop. So when we talk about a decider, that's when this is going to be much more interesting for us. So that's a wonderful question. So just to kind of connect this all together for us, when we get later on in this course, we're going to be interested in when the running time of this is in fact going to be a polynomial. So just when I say polynomial, I'm going to be referring to when I talk about big O of n to the k, where k is some constant. So this is some constant. We're going to be interested in that later on in this course. So that brings me to talking about one small but very interesting theorem that has its very much a important theoretical significance, is that if I tell you this, so I want to tell you how long it takes to simulate the other Turing machine. Just to make it clear, if I do n moves with the Turing machine, how long it will take, presuming the Turing machine actually halts. So there is just to be clear, a one-tape Turing machine that simulates n moves of a k tape. Now keep in mind, this k is not that k. It may as well just be like some other constant like c. Just to be clear, of a k tape Turing machine in big O of n squared time. So in quadratic time. So if you make n moves with the k-tape Turing machine, it takes quadratic time with the normal Turing machine. So just take note that if I go from the Turing machine to the multi-tape Turing machine, I'm still working with things that take polynomial time. That's the thing I really want you to take from this result. And the analysis for this comes from what I described over here. So again, you can find these details in one of the two books I mentioned. So that brings me to talk, remember, the big thing you really want to take from this is what stays polynomial. What stays polynomial is polynomial. But just keep that in mind. That's really the big thing I really want you to take note from this result. So when I talk about things later on in this course about complexity, sometimes we're going to be interested in things making sure that they stay polynomial like this. So notice that I make n moves. It translates to some quadratic number of moves for the other model. So I'll have more to say about that in a bit. So I want to move on to talking about another feature I'm going to build on top of this. And like I said, at the beginning of this course, I'm going to fancifully define machines that sound like pure magic to you. And this is going to be kind of like the grand poobah of one of them. That means basically the king of all of them, at least for most of the things I'm going to talk about in this course. There might be one other one I may have time to talk about. So let's move on over here. At least this is the king poobah of things that that I would say are the non-deterministic kind. And believe it or not, you will know most of the bits and pieces for it, which is very interesting in its own right. So I'm going to define for you a non-deterministic Turing machine. So, non-deterministic Turing machine. Non-deterministic Turing machine. I'm going to abbreviate this as NTM. To be clear, if ever I'm talking about a normal Turing machine, like the way I've been defining them and playing around with them, I'll call those deterministic Turing machines. I'll abbreviate those as DTM. Just to be clear. So the great part about this is it's defined in every way like a Turing machine. Like a Turing machine, except its transition function. Which is, and this should remind you of back when we've been defining our transition functions like this. I'm hoping that this will harken back to something that you've seen in the past. This is why I write it like this. So I'm going to assume I'm given a state, I'm given some tape symbol, and this will, so that's my input, some state, some tape symbol, and I'm going to get some subset, so I'm going to write the power set of the state, a tape symbol, and a left or right direction. So just to be more careful with the way I'm phrasing this for you. So this should remind me a lot of when I was talking about NFAs. So remember, I used this notation before. Just now, notice that this defines a triple. So this is the triple I had when I defined the Turing machine for you. So now instead of it being just, oh, I get some triple, now I'm going to get a subset of all possible triples. So it's very much like when we talked about an NFA. So just to be clear what I mean by this, that is for each state and tape symbol, we'll call it state Q, and tape symbol X, we're going to say delta of Qx is going to be equal to a set. So now it's a set of states we're going to have. We're going to have Q1, Y1, D1, Q2, Y2, D2, all the way up to some QK, YK, DK. And this is for some integer k. So they can differ in their size. It's just, this is just some k for some k greater or equal to 0. So just to be clear, these sizes of these sets can differ. I'm just saying that there is just some k such that I can list them like this for any one of these. So it's just going to be like when we talked about the NFA. Remember, the NFA, we had a set of states, right? And that's exactly how you should think about this. And that's why I showed you actually that first. Does everybody see that? So now notice that really all I've done is I've just given you the Turing machine, and now instead I have it so it gives you back a set of configurations. So you might ask, okay, what does that actually mean for us? Now this is where the magic of clairvoyance sort of kicks in. The non-deterministic Turing machine can choose at each step any of the triples for the next move. For the next move. For the next move. And you might naturally guess from what I've told you before, how is it going to be able to guess these things? Remember, it has when we're talking about this, it has the ability to know which path of execution leads to at least one accepting state. So, what do I mean by that? We say a language, L, is accepted or recognized by a non-deterministic Turing machine if for every W, every input W in the language, that there is any sequence of choices of moves that leads from an initial ID. So remember, that's an instantaneous description of the Turing machine. Initial ID with W as input, to some ID with a final state. That's all the non-deterministic Turing machine needs. So as long as there exists a sequence of choices of moves, so it can pick from these, as long as there's some pathway of decisions that it can make out of some set of possibilities, and it can find the final state, it accepts. That sounds quite incredible, isn't it? I want to describe to you in concrete terms what this means. And I'm going to give you one last theorem, and then that's how we're going to wrap things up. I'll leave an interesting tidbit for you, depending on how much time we have here, okay? So I want to describe to you how this works. So a non-deterministic Turing machine, its computation, and you might ask, okay, Dan, well, what does the computation of a non-deterministic Turing machine look like? And the first thing you might think of is, okay, I can always pick from one of these triples. Keep in mind, I can't mix and match them. I can only pick one of them. But keep in mind, I will try to pick one. If it leads me to an accepting state, it will know how to do that if it accepts. Like I said, it's like magic. But if it doesn't, it has the ability to try all of them. That means that there's going to be some possibilities where sometimes this Turing machine will in fact never halt. Just like with our regular Turing machine. But for certain kinds of Turing machines, the non-deterministic Turing machine will be much more like some exhaustive search. I want you to keep that in the back of your mind. So the non-deterministic Turing machine's computation is a tree where its branches correspond to different possibilities. Different possibilities for the non-deterministic Turing machine for moves, just to be clear. So I'm going to draw you a picture, and I'm going to state a theorem for you, and if you give me 2 minutes, I could summarize everything we've been up to this point so that we could get to our next chapter of the course. So let me just draw you a picture just to give you a flavor for how this would work. So let me just draw you a fun picture here. So I'm going to imagine I have some tree. Let's make it so it goes like this. Okay, so when the Turing machine will start up, it starts off with its initial ID. That corresponds to the tape at the beginning. And then whenever it makes a move, there's a couple ways you can think about it. You can think of it as it picks one of those triples and causing it to go down one of these pathways. So it branches. And if there exists, say, one of these sitting right here, that in fact leads to an accepting state, it will, in fact, go down that pathway, go make the moves that correspond to making these choices so that it could get to the accepting state. However, like I said, if it's just some general non-deterministic Turing machine, there may be some path that goes on and on and on and on forever. And I mean forever. So it just knows how to do this. It has clairvoyance. It's magic. So it knows the future. So the question, here's the theorem I want to present to you. I'm not going to have time to go into all the details about this, so I'm going to state it for you, and I'm going to give you the idea of how it works. And then I'm going to give you one last thing. Let Mn be a non-deterministic Turing machine. There is a deterministic Turing machine, MD, so that the language of the non-deterministic Turing machine, Mn, equals to the language of the deterministic Turing machine, MD. So, believe it or not, by adding all of this, all of these things that I've just done, you don't lose anything in terms of what you can recognize with a Turing machine. And I'll give you a sketch of how this works. Now, if you look at this tree, what's a way I could search this tree to find that? Does anyone have any ideas? Think back to anything involving graph algorithms. How can I discover that node there that I circled? Can somebody give me an algorithm that does that? Just any algorithm you can think of that works. Now, for anybody that's taken 340, I know you know one of these. Yeah, so I got two suggestions, breadth first search and depth first search. Those are the exact ones I'm thinking of. Now, here's where we have to be careful which one we pick. So if we pick depth first search, what could happen is I could imagine I could go down one of these pathways and I could never end. Meaning it could get stuck all the way, all down one of those bad pathways. Instead, I want to be a careful explorer of this tree, and I want to think about it instead like this. So when I'm here at the beginning, my Turing machine is going to have a couple of tapes. Depending on which proof you go with, 2 or 3 tapes. One is going to simulate a queue. So so the idea is you're going to simulate the non-deterministic Turing machine using a queue, where you're going to exhaustively explore the tree, kind of like backtracking. In fact, it's very much like that. So you start off where you have the initial ID in your queue. Then you're going to exhaust all of the possible moves that can happen onto the second tape, which is going to operate like scratch work, where you're going to perform the moves on the other tape. And each one of those you're going to put into the queue. And every time you dequeue, you're going to mark those symbols, just in the way I told you in a previous lecture. And once you've done that, you're going to have more in the queue. You're going to make 1 move. Then you may make 2 moves. And then you may hit 3 moves. And you'll hit this one right here. And once you hit that configuration that gets you the final state, then you could stop this process and say it accepts. So this is the general idea of actually how you could show the equivalency between these two. But here's the interesting fact. It's a big thing, big thing. Okay, notice here. When I do the non-deterministic Turing machine, it is able to know which one of these to take to get over here. So the number of moves the Turing machine makes is 1, 2, 3. However, how about our simulated Turing machine? So our deterministic Turing machine that's simulating the NTM. How long will this take? Now keep in mind, remember, I'm exhaustively searching this tree. Now, I'm not looking for an exact figure or anything like that. Is it going to be polynomial or is it going to be something more? I'll give you a hint. It starts with an E. It's going to be more, exactly. It's going to be exponential. In fact, it's going to take exponentially more moves to simulate the NTM using a DTM. So that's something I want you to notice, is that to simulate takes exponentially more moves. So the slowdown is exponential. So every time I make one move, I have to exhaustively branch out all of these. And it's based on the branching factor of this tree. So you can have it where they branch out like this quite a lot. And that's, well, obviously degrade this whole thing. But this is an interesting fact. And I'm hoping to plant this seed for you, this idea. We don't know how to do this faster. We don't know how to do it faster than going exponentially slower than the non-deterministic Turing machine. That is an open question. We're going to be touching upon this later on in the course. For some of you that may be familiar with something called P versus NP, this is related to that quite closely and intimately. Now, just to give you a quick thing, so hopefully you can see the parallels between the two. So this is one way I could simulate the NTM using a deterministic Turing machine. Like I said, the running time now, however, is much slower. Much, much, much slower than, for example, my translation from the regular Turing machine to the multitape Turing machine. And you might ask, okay, how did I simulate this queue? I used the multitape Turing machine. So just keep that in mind. That's actually how the proof plays out. So remember, I have a tape for simulating the queue, another tape for scratch work that I'm going to exhaust out the cases. Okay. Now, is it okay by any odd chance if I get 2 more minutes from you? If I get 2 minutes from you, I can summarize where everything is. If you have to go somewhere, please just go somewhere else, okay? If you have to go, please don't let me waste your time, okay? But if you have a couple more minutes, I want to summarize one last thing for you, because when we come back, we're going to be tackling one of the more fundamental questions in this course. So is that okay with everybody? Give me a thumbs up if we're okay with that. Just want to quickly get one last thing out of here. That way you have everything set up so that when we come back, we could start all nice and fresh for our next topic. So I know it's reading week next week, I know. But let me just summarize a couple quick things for you. I know. But I really just, this is why I ask, is that I don't want to be taking your time, okay? But I'm hoping that I'm touching on some pretty fundamental things that might interest you. So I just want to give you an idea of where we are right now in the course. So let me just summarize one last thing here for you. So where are we so far? So just to summarize our last bit of things here, where are we so far? So here's a summary of everything we've done up to this point. Here's a picture. So remember, we started off with the regular languages. Then I moved up to the context-free languages, right? Then I told you that there's even more languages out here. These are those recursive ones. Those are for the Turing machines that always halt. Those are the ones where we have the languages that are decided. Then we have the recursively enumerable ones. Outside of here, there may be more languages. We'll see about that. But this is, say, all of our languages that we have that are possible. So here's all of the classes we've looked at so far. Now, there's a couple that I wanted to touch upon quickly. Is that there are two classes of languages I did not talk about, but I want to make sure you're aware of them. The first one is what we call context-sensitive languages. Context-sensitive languages. So these are often abbreviated as CSL. Context-sensitive languages. So if you're wondering how you get these, so these are a superset of the context-free languages. So your CSLs, they're going to be sitting right about here. And CSLs are actually described by so-called linear bounded nondeterministic Turing machines. Now, you might ask, what the heck does that mean? What it means is that there's markers that are placed at the beginning and ends of a finite amount of the tape. So you don't have the full infinite amounts of tape left and right. You actually have only a constant factor amount of tape cells with respect to the input. So if I gave you 5 tape cells, it can only be a multiple of 5 beyond there that you can use. So it's like I'm bounding the space that you can use on the tape. That's what a linear bounded non-deterministic Turing machine is. Another class that I didn't tell you about is the so-called deterministic context-free languages. So these are described by what we call deterministic PDAs. So as the name suggests, you lost a lot of features of the PDAs. If you're curious, both the books I have I've suggested for reference do actually go into quite a bit of detail about these if you're curious about them. But if you're wondering, no, they don't describe actually, believe it or not, the same set of languages that the context-free ones do. They're actually a subset of them. So these are your deterministic context-free languages. And then naturally, you might ask, okay, well, what else is there? There's a lot of different classes of languages, but I just want to point out to you that there's something called the Chomsky hierarchy. So this is often used to describe the language, the relationships that different grammars have, but it's very often used to categorize different languages. And there's 4 different types. There's what we call type 0. So type 0 is the recursively enumerable languages. These are all possible ways you could describe a formal grammar to somebody. Type 1, this is the context-sensitive languages. These are the ones, so remember I told you about context-free languages, how it's always within the scope of the generated string that you have. Context-sensitive, you have the ability to control on the left and the right the context. Type 2, these are your context-free languages, naturally described by context-free grammars. And then type 3, you have your regular languages, which are described by so-called regular grammars. So what's next? What's next from here? Can we use Turing machines to describe any language? That's where we're going to be going with this. And in particular, are there going to be problems that we have no algorithm to solve them? So when we come back next day, we're going to start studying that aspect of computability. So I want to say thank you very much, and I thank you very much for the extra time to do this. I really appreciate it, and I think that this will go a little bit better than me recapping all of this after you come back. So have yourself a wonderful reading week, and I'll see you next time. Oh yeah, one other small thing. If you find yourself having any questions during reading week, I will be at my office hours. So if you find yourself wanting to come and bug me about things, I'll be there, okay? So have yourself a beautiful reading week, and thank you again.